Alright guys, hello and welcome back to another episode of Stonks Maxxing. Still day 112, but just came back from lunch, spent I think like an hour or 2 hours relaxing, doing some other stuff, but now I am back to it. So I kind of want to continue back where we were with our memory build out. And we had talked about there's three big players in the memory space: Micron, Samsung, and SK Hynix. And it seems like the big growth prospect for all three, or really any memory maker, is the idea of high bandwidth memory. And today, the generation of high bandwidth memory is on the 3E. I think E stands for extended, but this is going to be a type of memory that's going to be used for all of the next generation AI accelerators. So think Blackwell with NVIDIA, MI325X for AMD. I want to say Falcon Shores for Intel. Any of the new hyperscaler chips that are co-designed with Broadcom or even Marvel as well. And then also Qualcomm chips. I want to say, I don't know if Qualcomm actually has any of those AI accelerator chips. I think they're more towards the client, so the PC and the mobile segment, instead of high performance computing in the data center segment. So some of the big hyperscale names, you have tensor processing units from Google. You have the MTIA with Meta, although that isn't using high bandwidth memory. I think it's using low power double data rate 5. I want to say that is sort of this collection of DDR5 RAM chips on a single bus. I don't know if the right term is a bus, but it's on a single stick or on a single piece that has multiple sticks of RAM. So there's that. There's Amazon's Inferentia and Trainium. Might have already said that, but that does use high bandwidth memory 3E. And I'm going to say Apple has a co-designed chip with Broadcom. I don't know the details behind it. Could be worth looking into. Microsoft, they have their Maya chip, which I think is a CPU. I don't know if that also uses high bandwidth memory. Microsoft Maya chip. Maya 100, co-optimizing hardware and software from the ground up. And the start, transparency, and collaborative advancement have been core tenets in our design philosophy as we build and develop Microsoft's cloud infrastructure for compute and AI. Collaboration enables faster. So there's a software development kit. Okay, that's interesting. Yeah, I totally forgot about the software layer. Does he do AMD chips? What does run hot mean? Okay. CUDA. OpenCL. Rock M. I think that's what this is. Yeah, Rock M. Enterprise IT sales. Okay, it's a very interesting comment. Okay, so that's interesting. So they have Rock M. I actually think this is a very interesting. So it's called a kernel library, it seems like. .24. On die SRAM combined with 4 HBM 2E die. Okay. 2E HBM stack. So my imagination is 4 by 24. 424 gigs. So it'll be 16 gigabytes each, it seems like. 4 times 16 is 16 gigabytes, right? But 16 isn't divisible by 3, no? .8 TB per second. .700 watt TDP can deliver high performance while maintaining high proficiency. My collectives. Static random access memory at the close level. Yeah, I think that, so this is very good one. Will this release? Late 2024. Mafia. Okay, so I guess release date is still unconfirmed. 2024/2025 for now. Let's see. Microsoft Cobalt. So it's a CPU. Okay. So it's like cloud almost. Cloud. I guess it's a couple hundred CPU. Okay. Meta MTIA. And then Amazon Trainium. Bonk. Oh god. Just got a notification that Bonk is available to trade. Okay. Yeah, my MongoDB calls are getting cooked. Jesus Christ. Okay. MI 300. Oops. Future 16 training chips. So 3. Six terabytes, jeez. Okay, so Tranium chip 1500 divided by 16. By 36. Maybe 4. I could see that. So 4 gigabytes. Probably 8 high. Assuming. Sure. Neuron link. I guess 2 HBM. That's funny. 0.9 bytes per terabytes per second. I don't know what scale up versus scale out networking mean. Yeah, I have to understand what that means. What does scale up versus scale out mean in AI accelerator lingo? For example, so this is hurting my eyes. Stairs. Shooter training, okay. Got it. Patches of data to different nodes. Scale up, scale out. Terms to increase computational power. Yes, that's like the floating point for operations per second. Scale up, so they use the NVLink. By increasing, I don't know if it's like dies or chips. a chiplet. Design of the chips themselves, okay. Oh, Cerebrus, right? And infinity fabric, same. Try to solve. Same. Serve as interconnect technology. Try connections among GPUs in a single node. Increase computational power by increasing connections among multiple nodes. So first, remember scale Hynix 2013 probably. High bandwidth, this HBM2. Okay, this is cool. It's very helpful. October 2013, January 2016, August 2019, January 22, May 2023. So HBM4 then is expected So 3 years. 2026. Max data rate speed per pin. So I guess it's like the pin that we were talking about, each memory chip can have multiple pins, and I guess that connects with the CPU, so you probably need a pin to connect to a processor, and that's the way the information is exchanged, I'd imagine. 3.6, 6.4 beats. I don't know what the stack is referring to. HBM goals. Provide more bandwidth and throughput, I guess. Provide more bandwidth while taking on less power, thus decreasing the TCO. Okay, I am so tired right now. Oh my god. How's the stream going? Okay. I'm gonna go make myself a coffee. I'll be back. have retrieved my coffee. Alright. So I think what I want to do now, I've kind of hit this point where I'm kind of satisfied with this for right now, but I would love to learn a little bit about how this memory system works. I have like about an hour before my dad gets here. Him and I are gonna eat some dinner. So I kind of want to go to the branch education video. Let's see, branch education. Oh wow, okay, so they have, it's cool. Hard drive would be interesting. Starlink is also would be very interesting. Ooh, SSD. Yeah, that'd be very cool. Not sure which one I should watch first, the SSD or this NAND. Try this first.
Great. The new GoDaddy Arrow has AI marketing tools to help small...
Working memory. Accessing any section of...
Okay, so I wonder if I can follow along on my other computer here. Okay, and should I say this? So I want to go to Notion. And Anki. It's probably the best way for me to learn. It's going to be Anki. Okay. I'm trying to think about how I should structure this. I think this is good. I think this is good. Okay, so let's actually go back to the first.
Have you ever wondered what's happening inside your computer when you load a program or video game? Well, millions of operations are happening. But perhaps the most common is simply just copying data from a solid-state drive or SSD into dynamic random access memory or DRAM. An SSD stores all the programs and data for long-term storage. SSD into dynamic random.
What is one of the most common operations in takes place in a computer? Copying data from the solid state drive SSD into dynamic random access memory.
Random access memory, or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time, hence the loading bar. Because your CPU works only with data after it's been moved to DRAM, it's also called working memory or main memory.
Okay. So what are the different names for the data stored in DRAM? So the data Y is people call it that. Called working memory or main memory because it is the memory that the CPU reads from. Okay.
The reason why your desktop uses both SSDs and DRAM is because solid-state drives permanently store data in massive 3D arrays composed of 1 trillion or so memory cells, yielding terabytes of storage, whereas DRAM temporarily stores data in 2D arrays composed of billions of tiny capacitor memory cells in 2D
So these are, I think, transistors, then these are the capacitors that actually store the data. These are the transistors that turn on and off.
Arrays composed of billions of tiny capacitor memory cells, yielding gigabytes of working memory. Accessing capacitor memory cells, yielding gigabytes of working memory.
Yeah, so that's 108. Hmm. 16 gigabytes of data. This is a very good photo. I don't know what I should. Memory cells. Okay, so which form of data does SSD or DRAM have more? SSD or DRAM store more data? Usually SSD stores more data than DRAM. It's a permanent, so a permanent form of storage, of data storage. It usually has 5 to 10x amount of storage compared to DRAM for a
Accessing any section of cells in the massive SSD array and reading or writing data takes about 50 microseconds, whereas reading or writing from any DRAM capacitor memory cell takes about 17 nanoseconds.
Okay, so that is 1,000 times. Yeah, that's 1,000 times faster. Wow. Okay. Like 2,000 times faster, I think, actually. Is it faster to read or write from DRAM or SSD? It is faster to read/write from, often taking a few nanoseconds versus read/write from SSD, often taking a few microseconds. No. No. Snipping tool, please don't fail me. Let's go. So it is sometimes 3,000 times faster. DRAM versus SS. Faster is DRAM versus SSD. About 3 times faster, yeah. Approximately 3,000 times faster.
Which is 3,000 times faster. For comparison, a supersonic jet going at Mach 3 is around 3,000 times faster than a moving tortoise.
Okay, interesting. It's a good. So what? Is there a comparative speed? Similar way. Comparison of two things where the factor is 3,000 times faster. Same. It's about speed. Mach 3 jet versus a slow moving tortoise. Okay.
So the speed of 17 nanosecond DRAM versus 50 microsecond SSD is like comparing a supersonic jet to a tortoise. However, speed is just one factor. DRAM is limited to a 2D array and temporarily stores 1 bit per memory cell. For example, this stick of DRAM with 8 chips holds 16 gigabytes of data, whereas a solid-state drive of a smaller size can hold 2 terabytes of data.
Why is everyone spiraling about YouTube banning ad blockers? Chill, you can just use Pi. This is Pi. It's a
More than
I wonder if there's a breakdown of... Okay, so there is a memory cell breakdown. Ooh, okay, DIMMs, memory channels, crucials. Okay, so they do talk about the DRAM memory cell, reading from DRAM, writing to DRAM, refreshing DRAM. Row hits, timing parameters, 32 DRAM subarrays, sense amplifiers, actuator DRAM.
100 times that of DRAM. Additionally, DRAM of data, more than 100 times that of DRAM. Additionally, DRAM requires power to continuously store and refresh the data held in its capacitors. Therefore, computers use both SSDs and DRAM. And by spending a few seconds of loading time to copy data from the SSD to the DRAM, and then prefetching, which is the process of moving data before it's needed, your computer can store terabytes of data on the SSD and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state are moved from the SSD into DRAM, so any of it can be accessed in a few nanoseconds, which is why video games have DRAM capacity requirements. Just imagine.
Minimum, okay, so...
Without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into this 16 gigabyte stick of DRAM. Just in a second, the SLs, textures, and the processing data from programs that were preemptively...
Yeah, actually, I like that. I'm gonna try to write that down. When booting, starting up a video game, and what is going on under the hood when the load screen pops up? What is going on under the hood when a video game pops up? When a video game loading screen pops up. actually data being read from the SSD into memory, into main memory,
copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state are moved from the SSD into DRAM, so any of it can be accessed in a few.
So that data can easily be accessed by the program during runtime. Okay. Files, 3D models, textures, config files. This involves reading 3D models, textures, files. Nice.
Few nanoseconds, which is why video games have DRAM capacity requirements. Just imagine, without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into this 16 gigabyte stick of DRAM. First, we'll see exactly how the CPU communicates and moves data from an SSD to DRAM. Then we'll open up a DRAM microchip and see how billions of memory cells are organized into banks, and how data is written to and read from groups of memory cells. In the
There we go. So a stick of DRAM is a piece of silicon that holds multiple RAM chips.
process data from. First, we'll see exactly how the CPU communicates and moves data from an SSD to DRAM. Then we'll open up a DRAM microchip and see how billions of memory cells are organized into banks, and how data is written to and read from groups of memory cells. In the process, we'll dive into the nanoscopic structures inside individual memory cells and see how each capacitor physically stores one bit of data. Finally, we'll explore some breakthroughs and optimizations, such as the burst buffer and folded DRAM layouts that enable DRAM to move data around at incredible speeds. A few quick notes. First, you can find similar DRAM chips inside GPUs, smartphones, and many other devices.
Why is it called dynamic random access memory? I guess it can move. means the computer can't access any section of data with an equal amount of time if the data is read or write compared to any other section. CPU's SRAM, static RAM.
But with different optimizations. As examples, GPU DRAM, or VRAM, located all around the GPU chip, has a larger bandwidth and can read and write simultaneously, but operates at a lower frequency. And DRAM in your smartphone is stacked on top of the CPU and is optimized for smaller packaging and lower power consumption. Second, this video is sponsored by Crucial. Although they gave me this stick of DRAM to model and use in the video, the content was independently researched and not influenced by them. Third, there are faster memory structures in your CPU called cache memory, and even faster registers. All these types of memory create a memory hierarchy, with the main trade-off being speed versus capacity, while keeping prices affordable to consumers and optimizing the size of each microchip for manufacturing. Fourth, you can see how much of your DRAM is being utilized by each program by opening your computer's resource monitor and clicking on memory. Fifth, there are different generations of DRAM, and we'll explore DDR5. Many of the key concepts that we explain apply to prior generations, although the numbers may be different. Sixth, 17 nanoseconds is incredibly fast. Electricity travels at around 1 foot per nanosecond, and 17 nanoseconds is about the time it takes for light to travel across a room. Finally, this video is rather long, as it covers a lot of what there is to know around DRAM. We recommend watching it first at 1.25 times speed, and then a second time at 1.5 speed to fully comprehend this complex technology. Stick around.
What? Okay.
Because this is going to be an incredibly detailed video. To start, a stick of DRAM is also called a dual inline memory module, or DIMM.
Welcome to the ARC Venture Fund.
To date, to get very good venture.
And there are 8 DRAM chips on this particular module. A stick of DRAM is...
So, what is a stick of DRAM also called? So, a stick of DRAM is also called a dual inline memory module. Okay, so what are the trade-offs between different types of data storage in the memory hierarchy? So the trade-offs, there is always a trade-off between speed and capacity. Smaller data storage mechanisms. Okay, so faster data storage mechanisms have to sacrifice on data storage capacity. So, i.e. registers, CPU cache, memory, and storage. How fast is 17 nanoseconds? It is really fucking fast. About the give a practical comparison. Of lights traveling through a room. Oops.
Also called a dual inline memory module, or DIMM. And there are 8 DRAM chips on this particular DIMM. On the motherboard, there are 4 DRAM slots, and when plugged in, the DRAM is directly connected to the CPU via 2 memory channels that run through the motherboard.
Okay, so this means that this motherboard can contain 64 gigabytes, right? Because you have 16, and then 16 gigabytes per DIMM, and then you have 4 slots for each DIMM.
Note that the left 2 DRAM slots share these memory channels, and the right 2 share a separate channel. Let's move to look inside the CPU at the processor. Along with numerous cores and many other elements, we find the memory controller which manages and communicates with the DRAM. There's also a separate section for communicating with SSDs plugged into the M2 slots, and with SSDs and hard drives plugged into SATA connectors. Using these sections, along with data mapping tables, the CPU manages the flow of data from the SSD to DRAM, as well as from DRAM to cache memory for processing by the cores. Let's move back to see the memory channels. For DDR5, each memory channel is divided into 2 parts, Channel A and Channel B. These 2 memory channels, A and B, independently transfer 32 bits at a time using 32 data wires. Using 21 additional wires, each memory channel carries an address specifying where to read or write data, and using 7 control signal wires,
So that'll be 28.
commands are relayed. The addresses and commands are sent to and shared by all 4 chips on the memory channel.
Right, so the addresses are sent to and shared by all 4 chips on the memory, on the DIMM.
Channel, which work in parallel. However, the 32-bit data lines are divided among the chips, and thus each chip only reads or writes 8 bits at a time. Additionally, power for DRAM is supplied by the motherboard and managed by these chips on the stick itself. Next, let's open and look inside one of these DRAM microchips. Inside the exterior packaging, we find an interconnection matrix that connects the ball grid array at the bottom with a die which is the main part of this microchip. This 2 GB DRAM die is organized into 8 bank groups composed of 4 banks each, totaling 32 banks. Within each bank is a massive array, 65,536 memory cells tall by 8,192 cells across.
I can't even do that in my head.
Essentially rows and columns in a grid, with tens of thousands of wires and supporting circuitry running outside each bank. Instead of looking at this die, we're going to transition to a functional diagram, and then
Yeah, there's bank address inputs.
reorganize the banks and bank groups. In order to access 17 billion memory cells, we need a 31-bit address.
31-bit address. It's 2 to the 31. Really? What, 32? 2 to the 32. Okay.
To access 17 billion memory cells, we need a 31-bit address. 3 bits are used to select the appropriate bank group, then 2 bits to select the bank. Next, 16 bits of the address are used to determine the exact row out of 65,000.
Your brain lights up like a TV when you're playing video games. So check this out. Researchers from the University of California.
Because this chip reads or writes 8 bits at a time.
Okay, so the memory address then. Okay. So the memory address finds the bank. Maybe that's kind of like a street name or a city. And then it finds the street address, probably. Okay. How's the stream going? All right, nice, still going strong. So let's try to go back a little bit. There's
Any
some
other element channels. There are 8 DRAM chips on this particular DIMM. On the motherboard, there are 4 DRAM slots, and when plugged in, the DRAM is directly connected to the DRAM.
So how? How is DRAM placed onto a motherboard in a PC? DRAM is usually are placed on a DIMM, so dual inline memory module. Dual inline memory module that are then inserted into slots on a motherboard. Eight DRAM chips.
Slots, and when plugged in, the DRAM is directly connected to the CPU via 2 memory channels that run through the motherboard.
Okay, memory channels. How is DRAM connected to the CPU? So via memory channels, the motherboard.
Nodely connected to the CPU via 2 memory channels that run through the motherboard.
That run through the motherboard.
Note that the left 2 DRAM slots share these memory channels, and the right 2 share a separate channel. Let's move to look inside the CPU, and the right 2 share a separate channel. Let's move to look inside the CPU at the processor. Along with numerous cores and many other elements, we find the memory controller.
So how does a part of the CPU interacts with memory? So DRAM, the DRAM interface slash memory controller.
Which manages and communicates with the DRAM. There's also a separate section for communicating with SSDs plugged into the M2 slots.
SATA SSD interface.
And with SSDs and hard drives plugged into SATA connectors.
Okay, SATA. SSD and DRAM. Memory. The M2 slash SSD SATA SSD interface interacts with storage. Snipping tool. Whoops. I'm getting a call real quick. Let me get this real quick. Yeah, 我在家。It's okay, sure. I have some. Maybe a water bottle, like a. If there's a water bottle. 就是像有 reusable 那样的。没有。那我不要那个 plastic， 我可能像那个 cup or something。Yeah。可能吧，可能吧。Yeah, yeah, yeah， 没事，我在这儿有，我有。OK， 喂，妈回来。Oh wow, sorry. Okay. 喂，妈。Yeah, okay.喂，妈。你还想去纽约吗？还是不想去了？Yeah. Yeah, yeah. Sure. Yeah, 但是那都 Okay. 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 Yeah. That's it. Okay. Gonna have to go soon, but this picture is so fire. I don't know if you can see that, but god damn. Also, let's go, Wizards. Yeah, I gotta take a look at this. Oh, search the DRAM. They won. They won. Okay, damn. Hornets are 7-20 though. That's rough. Pistons aren't doing too bad actually. Okay, I'm gonna have to watch. Quick break.
For just 2 wins in their last 31 games.
Both teams struggling, so this is up for grab game if you ask me, and whoever has the most will come out on top, Chris.
All right, let's take a look at our starting lineup. It's presented by Popeyes. You see a lob upstairs from Ball. That's just a different NBA.
Danilfin is a stock analytics platform powered by artificial intelligence. Unlike traditional stock picking,
second chance opportunities here in this second half. Only allowed one offensive rebound.
Ball trying to get his offense going, and he does. Ends up in the hand of Ball down to Bridges. Bridges bumping his way inside. Mark Williams snatching the screws off the rim.
Might have been more than the screw, Chris. Who's having a hot hand? I think Corey Kisper's shot lights out. It's not in the ball game.
Poole, pure from distance.
Jordan Poole, if you get him going right.
I'm with you. A guy like Valanciunas, he's only played 15 tonight. Poole again. Back-to-back threes.
Hey, right there, that answers all questions. You got a guy.
5.5 to go in the fourth quarter. JP, nice pass inside. Sarr!
You get an L one?
Seth Curry rattles out a three, rebounded offensively by Charlotte. The lead to Cody Martin. Layup good.
And right there, you've done a good job limiting.
There's his turnover. Brogdon, Poole, lob to Koulibaly. Are you kidding? Wow!
Yeah, that's clean.
Lob to
Limiting.
There's his turnover. Brogdon, Poole, lob to Koulibaly. Are you kidding? Wow! Simichon. Brogdon has been the catalyst for the Wizards bench tonight. Sarr tickles the twine.
Alex Sarr with a huge.
Found by Diabate. Done some yeoman's work, making LaMelo Ball a volume shooter. Diabate free and clear. Here's Sarr. Kick out. Koulibaly swinging it over to Brogdon. Smart basketball decision by Koulibaly as Brogdon. Now
Take your time, go run up there, set a solid pick right here, stationary, and let him go downhill. Okay, you
kick it out to Sarr. To close the show! Alex Sarr! Indeed! Bridges going right. Oh, monster slam. It's been a dunk fest here in the district.
This has been an exciting ball game. Thanks, Paul Evans.
I didn't mean to hate on you, brother. There's a turnover. Here comes Martin. Another slam.
That's 108.
Offensive rebound by Martin.
Oh, wow.
Ball.
That's insane.
That's 108.
Offensive rebound by Martin.
Oh, wow.
Ball. New look Capital One Arena in the next 3 years. Bridges misses. Sarr will secure a rebound, and Washington will secure victory.
All right, that's good. That's good.
Using these sections, along with data mapping tables, the CPU manages the flow of data from the SSD to DRAM mapping table.
Data mapping tables. Okay, I don't know what that
The
is.
CPU manages the flow of data from the SSD to DRAM, as well as from DRAM to cache memory for processing by the cores. DRAM, as well as from DRAM to cache.
Okay, so I guess this is how the memory hierarchy stuff works. Into DRAM memory dynamic to CPU cache
memory for processing by the cores. Let's move back to see the memory channels. For DDR5, each memory channel is divided into two parts, channel A and channel B. These two memory channels, A and B, independently transfer 32 bits at a time.
Okay, so I have to see what that means. DDR5 memory channels. Okay, so into two independent 32-bit addressable subchannels to increase efficiency and lower latencies of data for the memory controller. Any memory channels does DDR5 DRAM have?
Using 32 data wires. Using 21 additional wires, each memory channel carries an address specifying where to read or write data.
Dual inline memory module has two independent. Data bus is a collection of electrical pathways, wires, or traces used to transfer data between components in a computer, such as the CPU, memory, and other peripherals. The width of a data bus indicates how many bits of data can transfer in a single clock cycle. Width is measured in bits, 8 bits, 16 bits, 32 bits, not physical dimensions. Okay. Yeah, interesting. Bathroom time. Oops.
Data, and using 7 control signal wires, commands are relayed.
21 wires. Wait, let me see.
And B, channel A, 5. Each memory channel is divided into 2 parts. Channel A, 5. Let's move back to see the memory channels. For DDR5, each memory channel is divided into 2 parts, channel A and channel B. These 2 memory channels, A and B, independently transfer 32 bits at a time.
Okay, so independently transfer DDR5 DIMM tab. There are 2 independent memory channels, A and channel A and channel B.
A and B independently transfer 32 bits at a time using 32 data wires.
Okay. How much data can they transfer? I guess per cycle. Per cycle. Each memory channel can transfer 32 bits of data using 32 data wires, which I guess is some type of connection. Motherboard. So dual inline memory module data wires, memory channel. So these are, I guess data wires are just connections between the DIMM and CPU. Okay, so independent channels, memory channels, and then 32 bits of data being transferred.
Using 21 additional wires, each memory channel carries an address specifying where to read or write data, and using 7 control signal wires, commands are relayed.
Control signal.
The addresses and commands are sent to and shared by all 4 chips on the memory channel, which work in parallel. However, the 32-bit data lines are divided among the chips, and thus each chip only reads or writes 8 bits at a time. Additionally, power for 32-bit chips on the memory channel, which work in parallel. However, the 32-bit data lines are divided among the chips, and thus each chip only reads or writes 8 bits at a time.
How much capacity can RAM chips have? I guess DRAM chips have. Up to 32 gigabytes per chip. DRAM modules with capacities up to 1 terabyte. Wow. Okay, that's a lot.
Additionally, power for DRAM is supplied by the motherboard and managed by these chips on the stick itself. Next, let's open and look inside one of these DRAM microchips. Inside the exterior packaging, we find an interconnection matrix that connects the ball grid array at the bottom with a die, which is the main part of this microchip. This 2 gigabyte DRAM die is organized into 8 bank groups, composed of 4 banks each. Total.
Okay, so bank groups and then a bank.
32 banks.
So I'd say a bank group is probably the same thing as maybe an index and a cache, and then the tag is. No. Maybe a bank group would be like a state. I'm trying to connect this to something that I know. Bank group is a state, a bank is a city, and then a specific capacitor could be the address.
Within each bank is a massive array, 65,536 memory cells tall by 8,192 cells across, essentially rows and columns in a grid, with tens of thousands of wires and supporting circuitry running outside each bank. Instead of looking at this die, we're going to transition to a functional diagram.
So what is the layout of a DRAM die? Oh god, just choked on my spit. Okay, a DRAM die is organized into bank groups. Think the bank groups then are collections. So each bank group holds a handful of banks, consists of a collection of banks, then each bank is a large array. Think bank group equals state. So large array. Oops. array is equal to home address. Bank is equal to city. Oops. Bank group 8 on 2 gigabyte DRAM chip. Okay, and then bank. So there's 4 per bank group on a okay, and then
RAM, 72 cells, 36 memory cells, top or 2 gigabyte DRAM die is organized into 8 bank groups, composed of 4 banks each, totaling 32 banks. Within each bank is a massive array, 65,536 memory cells.
Massive array, so 605, 6 by
tall by 8,192 cells across.
8192 memory cells on a 2 gigabyte DRAM chip. I guess zip code. Each array stores has a collection of memory cells. Memory cell, so that is equal to your home address.
Across, essentially rows and columns in a grid, with tens of thousands of wires and supporting circuitry running outside each bank. Instead of looking at this die, we're going to transition to a functional diagram, and then reorganize the banks and bank groups. In order to access 17 billion memory cells, we need a 31-bit address. 3 bits are used to select the appropriate bank.
Okay, so there's 3 bits for 8 bank groups, right? That makes sense. And then 2 bits probably for selecting the actual bank within each
group. Then 2 bits to select the bank. Next.
Oh. Okay. And then if we have, let's take a look. If there's (8,192) columns, rows, so 1024 8 times 8, so maybe 13 bits to get the column.
16 bits of the address are used to determine the exact row out of 65,000. Because this chip reads or writes 8 bits at a time, the 8,192 columns are grouped by 8 memory cells, all read or written at a time or by 8, and thus only 10 bits are needed for the column address, time, or by group.
Wait, let's see. So log base 2 of, okay, 16. All right.
By 8 memory cells, all read or written at a time or by 8, and thus only 10 bits are needed for the column address. One optimization is that this 31-bit address is separated into 2 parts and sent using only 21 wires. First, the bank group, bank, and row address are sent, and then after that the column address. Next, we'll look inside these physical memory cells. But first, let's briefly talk about how these structures are manufactured, as well as this video's sponsor. This incredibly complicated die, also called an integrated circuit, is manufactured on 300mm silicon wafers, 2,500-ish dies at a time. On each die are billions of nanoscopic memory cells that are fabricated using dozens of tools and hundreds of steps in a semiconductor fabrication plant, or fab.
I had no idea my old ad blocker was installing malware on my computer. That's why I got Pi. This is Pi.
This one was made by Micron, which manufactures around a quarter of the world's DRAM, including both NVIDIA's and AMD's VRAM in their GPUs. Micron also has its own product line of DRAM and SSDs under the brand Crucial, which, as mentioned earlier, is the sponsor of this video. In addition to DRAM, Micron is one of the world's leading suppliers of solid-state drives, such as this Crucial P5 Plus M2 NVMe SSD. By installing your operating system in video games on a Crucial NVMe solid-state drive, you'll be sure to have incredibly fast loading times and smooth gameplay. And if you do video editing, make sure all those files are on a fast SSD like this one as well. This is because the main speed bottleneck for loading is predominantly limited by the speed of the SSD or hard drive where the files are stored. For example, this hard drive can only transfer data at around 150 megabytes a second, whereas this Crucial NVMe SSD can transfer data at a rate of up to 6,600 megabytes a second, which, for comparison, is the speed of a moving tortoise versus a galloping horse. By using a Crucial NVMe SSD, loading a video game that requires gigabytes of DRAM is reduced from a minute or more down to a...
Yeah, okay, so that's like a speed up factor, I guess. This is maybe when you're comparing 2 systems. 2 to 3 seconds. That's a 20 times speed up, right?
A couple of seconds. Check out
to 30 times speed up.
the Crucial NVMe SSDs using a link in the description below. Let's get back to the details of how DRAM works and zoom in to explore a single memory cell situated in a massive array. This memory cell is called a 1T 1C cell and is a few dozen nanometers in size. It has 2 parts, a capacitor to store 1 bit of data in the form of electrical charges, or electrons, and a transistor to access and read or write data. The capacitor is shaped like a deep trench dug into silicon and is composed of 2 conductive surfaces separated by a dielectric insulator or barrier just a few atoms thick, which stops the flow of electrons but allows electric fields to pass through. If this capacitor is charged up with electrons to 1 volt, it's a binary 1. And if no charges are present and it's at 0 volts, it's a binary 0. And thus, this cell only holds 1 bit of data. Designs of capacitors are constantly evolving, but in this trench capacitor, the depth of the silicon is utilized to allow for larger capacitive storage, while taking up as little area as possible. Next, let's look at the access transistor and add in two wires. The word line wire connects to the gate of the transistor, while the bit line wire connects to the other side of the transistor's channel. Applying a voltage to the word line turns on the transistor, and while it's on, electrons can flow through the channel, thus connecting the capacitor to the bit line. This
I guess bit line is like the highway.
allows us to access and charge up the capacitor to write a 1 or discharge the capacitor to write a 0. Additionally, we can read the stored value in the capacitor by measuring the amount of charge. However, when the word line is off, the transistor is turned off, and the capacitor is isolated from the bit line, thus saving the data or charge that was previously written. Note that because this transistor is incredibly small, only a few dozen nanometers wide, electrons slowly leak across the channel, and thus, over time, the capacitor needs to be refreshed to recharge the leaked electrons. We'll cover exactly how refreshing memory cells works a little later. As mentioned earlier, this 1T1C memory cell is one of 17 billion inside this single die, and is organized into massive arrays called banks. So let's build a small array for illustrative purposes. In our array, each of the word lines is connected in rows, and then the bit lines are connected in columns. Word lines and bit lines are on different vertical layers, so one can cross over the other, and they never touch.
Word lines and bit lines.
Let's simplify the visual and use symbols for the capacitors and the transistors. Just as before, the word lines connect to each transistor's control gate in rows, and then all the bit lines in columns connect to the channel opposite each capacitor. As a result, when a word line is active, all the capacitors in only that row are connected to their corresponding bit lines, thereby activating all the memory cells in that row. At any given time, only one word line is active because if more than one word line were active, then multiple capacitors in a column would be connected to the bit line, and the data storage functionalities of these capacitors would interfere with one another, making them useless. As mentioned earlier, within a single bank there are 65,536 rows and 8,192 columns, and the 31-bit address is used to activate a group of just 8 memory cells. The first 5 bits select the bank, and the next 16 bits are sent to a row decoder to activate a single row. For example, this binary number turns on the word line row 27,524, thus turning on all transistors in that row and connecting the 8,192 capacitors to their bit lines, while at the same time the other 65,000-ish word lines are all off. Here's the logic diagram for a simple decoder.
Yeah, I don't know what the D stand for.
The remaining 10 bits of the address. Here's the
Or any of the A, so 2 to 4.
Logic diagram for a simple decoder. The remaining 10 bits of the address are sent to the column multiplexer. This multiplexer takes in the 8,192 bit lines on the top, and, depending on the 10-bit address, connects a specific group of 8-bit lines to the 8 input and output I/O wires at the bottom. For example,
To memory channels / CPU.
if the 10-bit address were this, then only the bit lines 4,784 through 4,791 would be connected to the I/O wires, and the rest of the 8,000-ish bit lines would be connected to nothing. Here's the logic diagram for a simple multiplexer.
So the multiplexer chooses which rows, or I guess which columns then to send. So and
We now have the means of accessing any memory cell in this massive array. However, to understand the 3 basic operations, reading, writing, and refreshing, let's add 2 elements to our layout. A sense amplifier at the bottom of each bit line, and a read and write driver outside of the column multiplexer. Let's look at reading from a group of memory cells. First, the read command and 31-bit address are sent from the CPU to the DRAM. The first 5 bits select a specific bank. The next step is to turn off all the word lines in that bank, thereby isolating all the capacitors, and then pre-charge all 8,000-ish bit lines to 0.5 volts. Next, the 16-bit row address bit line, isolating all the capacitors, and then pre-charge all 8,000-ish bit lines to 0.5 volts. Next, the 16-bit row address turns on a row.
Looking for what comes next? For that moment when everything finally...
And all the capacitors in that row are connected to their bit lines. If an individual capacitor holds a 1 and is charged to 1 volt, then some charge flows from the capacitor onto the 0.5 volt bit line, and the voltage on the bit line increases. The sense amplifier then detects the slight change or perturbation of voltage on the bit line, amplifies the change, and pushes the voltage on the bit line all the way up to 1 volt. However, if a 0 is stored in the capacitor, charge flows from the bit line into the capacitor, and the 0.5 volt bit line decreases in voltage. The sense amplifier then sees this change, amplifies it, and drives the bit line voltage down to 0 volts or ground. The sense amplifier is necessary because the capacitor is so small and the bit line is rather long, and thus the capacitor needs to have an additional component to sense and amplify whatever value is stored. Now, all 8,000-ish bit lines are driven to 1 volt or 0 volts, corresponding to the stored charge in the capacitors of the activated row, and this row is now considered open. Next, the column select multiplexer uses the 10-bit column address to connect the corresponding 8-bit lines to the read driver, which then sends these 8 values and voltages over the 8 data wires to the CPU. Writing data to these memory cells is similar to reading, however with a few key differences. First, the write command, address, and 8 bits to be written are sent to the DRAM chip. Next, just like before, the bank is selected, the capacitors are isolated, and the bit lines are pre-charged to 0.5 volts. Then, using a 16-bit address, a single row is activated, the capacitors perturb the bit line, and the sense amplifiers sense this and drive the bit lines to a 1 or 0, thus opening the row. Next, the column address goes...
There's a lot here. I'm going to have to go back to this. I am kind of curious. Wait, is this a... Okay, there's a CPU. How do clocks work? Or how are microchips made? So this is...
How many calculations do you think run what's called embarrassingly parallel up Bitcoin and the lottery? That's pretty much it for graphics cards. We're thankful to all our Patreon and YouTube membership sponsors. GDDR7 uses 3 different encoding schemes to combine binary bits in a video game. Different chunks of scene are continuously memory that surrounds AI chips. HBM is built from stacks of DRAM memory chips and uses TSVs, or through silicon vias, to connect the stack into a single chip, essentially forming a cube of AI memory. For the latest generation of high bandwidth memory, forward to the high-speed memory bytes, sure it uses Micron's HBM3E, which uses 30% less power data center, $25,000 to $40,000 memory, or Micron's next. Micron is...
Okay, yeah, I'm definitely going to have to watch that later. This is going to be a cool one. But let's see. There's also... this I definitely want to watch and finish. Engineering inside an SSD. Maybe this would be interesting.
Now you can get a great deal at the Hyundai Getaway sales event. Make your next getaway your best.
On the charge strap, it's a 0 episode. Understanding this, its charge strap turns on. This is because the electrons in the charge strap, as if we did cells,
this is even more
and read the megabytes of data.
Okay.
On the charge strap, it's a 0. Visualize and understand the
And flash, let's see.
This video is sponsored by Kioxia of Massachusetts, or 3 coins, and the controller, the upper page. You might wonder, how does the controller keep track? Kioxia sells a wide variety of SSDs, and the one we're using here.
Okay, so static random access memory, so it's SRAM. Okay, nice. I am going to charge this up, and then go use the bathroom. Okay, let's see, how is this live stream, by the way? All right, no one is watching. I'm gonna take a look at something real quick before I go use the bathroom. So Rock Creek. Damn, okay, that is way too long. 16.9 miles, damn. Okay, yeah, that's pretty rough. To the Strathmore. Huh. Holy fuck. Okay. Apparently this Rock Creek Trail goes all the way from... Oh, wow. Okay. Actually, I might have to go right now. Let me take a look. Hello? Okay, I'm coming. Okay, sounds good. Alright, thanks. Alright, bye. Yeah, I gotta go pick up my dad right now, so... Thank you for tuning in to the stream. This was fun. Learned a lot about DDR5, Dynamic Random Access Memory. I can see why it's so important now. And it's crazy that it's like I want to say Samsung had around 20 billion in sales of DDR5 though, or just DRAM in general. I think Micron had around 6,000 in sales. SK Hynix I think was around 6,000. But it seems like it's $10+ billion market. Oops. SK Hynix 7 billion, 7.8 billion, 8.7 billion. Okay, so Micron was 6 billion, 6.4 billion. Samsung was around 22. So with that, catch you guys in the next one. Peace.